Our next speaker is Kim Morgan de Oliveira, Porto, from UNESP, São Paulo State University. She will show a use case of deep learning to detect domain names for malicious use. And this is a pre-recorded presentation. So let's start.
Good morning, everyone. It's very exciting to be here at OARC 44. My name is Kim, and I'll be your speaker this morning. I'll be presenting our project, DGA Domain Detection and Classification with Passive DNS and Deep Learning. So, as you already know, DGAs, or domain generation algorithms, are methods used by most botnets to automatically generate domain names, to be used for hosting command and control servers and maintaining communication between infected hosts and a threat actor. The way this works is, an infected host uses a domain generation algorithm to create a large list of domain names. It then attempts to resolve each one of these domains until it encounters an active C2 server, establishing communications between an infected host and a threat actor. In this way, DGA domains abuse the DNS infrastructure to maintain communication with infected hosts, while evading detection and prosecution. When you take one DGA domain down, another one springs up to take its place. Our project aims to create a system that proactively detects these generated domains, so that they can be caught and blocked automatically before they are ever used by a threat actor. We have chosen deep learning as our method to detect these domains. Why is that? Deep learning is a particularly suitable solution for this problem, since each domain generation algorithm is different. As you can see here, we have 3 generated domains, and they're very different from each other. This one is a word list, this one is a large collection of random characters, this one is a small collection of random characters. In traditional classification methods, we would have to use feature engineering to manually discover what makes each one of these domains unique and different from the legitimate domains, which is both time-consuming and inefficient. Deep learning is a much more suitable solution to this problem, since it does not require feature engineering and can precisely detect the specific patterns that make DGA domains unique automatically. This project involved the development of 2 deep learning models. The detector model, as you can guess, is used to classify the input domain as legitimate or DGA. It's basically used to detect DGA domains in the wild. The detector model classifies domain names as legitimate or DGA using a convolutional neural network that analyzes domain names as the ASCII codes of each character through an embedding layer, classifying them as legitimate or DGA. The classifier model is used to classify a domain into a threat class and a DGA family. It uses a deep convolutional neural network and natural language processing that analyzes the domain name through character-level embeddings to classify the DGA family a domain belongs to, while also incorporating transfer learning to enable the introduction of new DGA families without affecting existing class performance. To apply these models in a real-world scenario, we applied this method on passive DNS data to analyze and identify DGA domains within our own organization's network. This prevents overfitting and avoids creating bias within our own models, as the results of our model will reflect real-world data. To achieve this, we started a federation to collect passive DNS data within our own organization, which is currently collecting queries across the whole of São Paulo State University. Currently, there are over 3.5 billion queries in our database, which grows every day. We use Entrada, a project developed by our friends at Sitting Labs, who you may know, to store all of our queries in Parquet formats, optimizing disk space and query time. So, how does everything I talked about come together? The passive DNS data that we have been collecting is used as training data for our models, whose accuracy is evaluated using DGA threat intelligence feeds. Here, we use DGA Archive, Spamhaus, and Cloudflare. We then display all of the domains our models have detected and classified inside of graphical dashboards, displaying our data in an actionable interface for our user. So, let's explain how the pipeline of our system works in execution. All queries from the collected passive DNS data is piped through the detector model, which classifies the requested domain as legitimate or DGA. If the domain is classified as legitimate, it is flagged as such and put into the undetected category. If the domain is classified as DGA, it is run for the classifier model, which classifies it into a particular family and gives it a threat score, We then check for the presence of the particular domain in one of our threat intelligence feeds. If the domain is present in one of them, it is listed as detected and listed. If the domain is not present in one of these databases, it is put into a quarantine zone where it's detected but unlisted. For 90 days, every day, we will check if these domains do appear in the threat intelligence feeds, which often happens, and they are moved into this category. Finally, all the categories and additional data is displayed to the user in graphical dashboards. As you can see, our system is only trained on real-world data and is only validated through real intelligence feeds. This avoids many of the common pitfalls of modern artificial intelligence articles, where models are overfit to training data and perform poorly on the real world. Our system is trained on real data and operates in a real scenario. So, let's have a look at how the system actually works through a live demonstration. This is a live instance of our system here. Here we have all of the domains in our passive DNS divided into the categories that we have just described. Here, we can see the detected and unlisted domains are so-called quarantine zone. Here we can see the detected domains, their risk score, the malware family they've been associated to, the days they've been in quarantine, etc. In this graph, we can see how many days each domain has spent in quarantine. We can see how the graph fluctuates a lot, as the domains are eventually detected in threat intelligence feeds and moved into the other category. Speaking of which, this is the detected and listed category. These are domains that have been detected in our data and have been flagged by threat intelligence feeds. We have the same data as before, their risk score, associated malware family, etc., alongside the threat intelligence feed that has flagged the domain. We can also see the proportion of flagged domains by threat intelligence list. Unsurprisingly, DGA archive have the most detected domains. We can also see the IPs that these domains resolve to. Just give it a minute, there's a lot of queries. Here we go, these are both IPs associated with this domain. And we can see other domains that are associated with this IP. Here we go. We can see a lot of domains associated with this IP, and they are all very similar. They all look like a DGA cluster. So, by blocking this IP, we can block this C2 server from our entire network, even though it's using a DGA system. We can also see here in this graph how many days each domain has spent in quarantine before they were moved into this category. These are all domains we have detected as DGA before they were ever flagged by any threat intelligence feed. Most of them spent about 1 day in quarantine before they are ever flagged by threat intelligence feed manually and added to the lists, but we also have some stragglers along the way. The amount of domains in this graph is indicative of the efficacy of our models, since these are real DGA domains that we have managed to catch before they are ever flagged and added to the lists. We are currently using all of this data in a wide variety of ways to tackle the presence of DGA domains in our network. By checking these dashboards, we have blocked a large number of detected domains and public IPs, reducing the quality of service of botnets inside of the network and potentially rendering them unviable. We have also used passive DNS data to identify clients querying the domains, subsequently discovering infected machines within our network. And we have identified strains of malware, which are most likely to be plaguing our network, enabling us to take measures specific to that singular malware family. In these and many other ways, the system we have developed allows for the preemptive detection of infected hosts inside of a network, allowing proactive measures to be taken and strengthening network security. At this stage, our deep learning models are pretty much completed, while the passive DNS integration and our dashboard are advancing towards completion. The passive DNS integration is ongoing as we are working towards establishing new members to our DNS federation. The monitoring dashboard is at an advanced stage, where we are working towards query optimization and displaying more data in new, actionable ways. Our project has had 2 distinct publications. An article describing the implementation of the detection model that we showed was published at the 26th International Conference on Enterprise Information Systems, which is a yearly conference concerned with advances and applications of information systems. while our classifier model has been published in an MDPI Applied Sciences journal, high visibility open access journal. In conclusion, the system developed within this project has managed to detect DGA domains in real network traffic, avoiding AI overfitting and bias. It has managed to detect DGA domains before they are ever flagged in threat intelligence feeds. It has managed to identify unreported command and control servers via cross-referencing, and it has managed to identify infected clients inside the network. With this, our system allows the detection of bad actors, allowing for proactive measures to be taken before a security incident ever occurs. These are our references. We can be reached at any of these emails appearing on screen, and we would like to thank you for your attention.